In this problem, we explore the birthday problem in the setting where not all days of the year are equally likely to be someone's birthday. So we're given this vector p that contains the probability of each day of the year being someone's birthday. And we're also given this definition of the kth symmetric elementary polynomial in the values, let's say x1 to xn. And the way to understand this polynomial is we take n choose k tuples, multiply their values, sum up the results. As an example, if we cared about the second elementary polynomial in the values, let's say x1 to x3, we would take the 3 choose 2 pairs, multiply their values, and sum them up. So that would be x1 times x2 plus, let's say, x2 times x3 plus x1 times x3. So this is how the elementary symmetric polynomials work. Now, given these definitions, in the first part, we're asked to find the probability of at least one birthday match. And we need to do this in terms of our vector p and the elementary kth symmetric polynomial. Now, let's first consider how these days might get assigned to k people such that there is no birthday match. So one such assignment of days might be, well, let's pick day 1, let's pick day 5, let's pick day 17, and so we're picking k days, and for the k, let's pick day, let's say, 312. This is a k tuple. These are unique values. So what is the probability? That these k days occur as the k people's birthdays? So that's the probability that someone's born on the first day times the probability someone's born on the 5th day times the probability someone's born on the 17th day probability someone's born on the 312th day. Now notice that for this k days that we've selected, each permutation of these k days is also a valid assignment of birthdays, right? The first person might be born on the 5th day, the second person on the 1st day, the third person maybe on the 312th day. So all the permutations of these k days are valid. So we need to multiply this value here, this product of our probabilities, by k factorial. So, okay, let's pick another k days, another unique k tuple. So this could be maybe 2, 16, 14, let's say 150. And what is the, and again, notice that any k factorial of the permutations of these days is a valid assignment of birthdays. And what is the probability of one such assignment? Well, that's the probability that someone's born on the 2nd day times the probability someone's born on the 16th day, 14th day, 150th day. And we can keep going. So how many such k tuples can we pick? Well, there are going to be 365 choose k such k tuples. So if we take these k tuples, if we take these values here and sum them up, then what we get is the probability of there being no birthday matches. Now from here we can factor out our k factorial, and we're left with p1, p5, p17, p312 plus p2, p16, p14, p150 plus etc., where here we have exactly our 365 choose k unique k tuples. So notice that what we have here, these products here, these are exactly k unique values selected from our vector p. These values are multiplied and then the results are added. This is exactly what we said the definition of the kth symmetric elementary polynomial was in these n values. In our case, n is 365. So the sum here then is equal to the kth elementary symmetric polynomial in the vector p, because these values are coming from the vector p. And if this was equal to the probability that there are no birthday matches, and we are interested in the probability of at least one birthday match, we need to subtract that value from 1. And we get our answer for part A. Now for part B, we want an intuition as to why the probability of at least one birthday match would increase if the pi's in the vector p were not all the same. And the intuition is as follows. So suppose pi is larger than pj for some I not equal to j. So we have our vector p, and suppose one of the values in that vector is larger than some other value. So then, what does this mean? That means the ith day is more likely to occur as someone's birthday compared to the jth day. Compared to the jth day, which means that it is more likely that we have birthday matches, specifically for day I, because day I is more likely than day j, right? It is more likely that people were born on day I than day j. So it is more likely that we have birthday matches specifically for that day I. So that is the intuition as to why we want these all these pi values to be the same to minimize the probability of at least one birthday match. So now we'll prove that more rigorously by using two things. The first thing we'll use is the AM-GM inequality, arithmetic geometric mean, which states that the average of these two values, x and y, the arithmetic average is greater or equal to what's known as the geometric mean. And then the second thing we'll use is the property of these elementary symmetric polynomials, which states that the kth elementary symmetric polynomial can be rewritten in this way. So x1 times x2 times the k minus second elementary symmetric polynomial in the values from x3 up to xn plus x1 plus x2 times the k minus 1th elementary symmetric polynomial in the values x3 to xn plus the kth symmetric polynomial in the values x3 to xn. So we're going to use these two properties. Now, what we're asked to do is the following. So we're given this vector r that is the same as vector p except for the first two values. And the first two values are the average of the two values in p. So this is p1 plus p2 over 2. And the second value also is p1 plus p2 over 2. Everything else is the same as in p. P365. And what we're asked to prove is that the probability of at least one birthday match given our original vector p is bigger or equal to the probability of at least one birthday match given the vector r, implying that whatever assignment of birthday probabilities for this 365 days, whatever assignment you give me, I'm going to replace two of those values with the average of those two values. And what I'll get, and I'll potentially reduce the probability of getting a birthday match. So this is what we need to prove. Well, let's look at let's rewrite this expressions. In part A, we said that the probability of at least one birthday match is 1 minus k factorial, the kth elementary symmetric polynomial in P, and the left side is, or the right side is 1 minus k factorial, the kth elementary symmetric polynomial in R. So if we want to show, so we need to show this, so if we need to show this inequality, so the left-hand side is greater or equal to the right-hand side, it suffices to show that the kth elementary symmetric polynomial in P is less than or equal to the kth elementary symmetric polynomial in R. Now, so this is now what we need to show. So to show this, we're going to use the property that we talked about, the property of the kth elementary symmetric polynomials. So notice that this term here does not use the first two entries of the P vector or the R vector. It only starts using from the third value and on. So these values are going to be the same for, these values will be the same for the kth elementary symmetric polynomial in P and the kth symmetric polynomial in R, because they only use the values in those vectors starting from the third position. Now, for this term here, notice that R1 plus R2 is the same as P1 plus P2, because R1 and R2 are the average of P1 and P2. And so this term here is also the same for the elementary symmetric polynomial in P and the elementary symmetric polynomial in R. So the two elementary symmetric polynomials only differ in this term here. So comparing the two elementary symmetric polynomials, boils down to comparing R1, R2, k minus second elementary symmetric polynomial from x3 to xn, and P1, P2, k minus second elementary symmetric polynomial. Well, these are actually R's here, so this is R3 to Rn, P3 to Pn. But notice that P3 to Pn are exactly the same as R3 to Rn. So this actually boils down to just comparing R1, R2 and P1, P2. Now recall that R1 equals R2 equals P1 plus P2 over 2. So R1 times R2 is the square of P1 plus P2 over 2. And by the arithmetic mean geometric mean, we know that the square of P1 plus P2 over 2 is bigger or equal to the square of the square root of P1, P2. But the square of the square root of P1, P2 is just P1, P2. So we see that R1 times R2 is greater or equal to P1 times P2, which implies that the kth elementary symmetric polynomial in R is bigger or equal to the kth elementary symmetric polynomial in P, which in turn implies that 1 minus k factorial, kth elementary symmetric polynomial in P, is smaller or equal to 1 minus the kth elementary symmetric polynomial in R. So we showed that the probability, or sorry, this is a larger or equal to. So this is since the kth elementary symmetric polynomial in R is bigger or equal to the kth elementary symmetric polynomial in P, when we subtract this smaller value from 1, we get something larger or equal to 1 minus k factorial kth elementary symmetric polynomial in R. So recall that this expression is the probability of at least one birthday match given P. And we just showed that this is bigger or equal to the probability of at least one birthday match given R. And as we said, what this implies is if you give me some vector P of probabilities of these days being birthdays, I can take any two of them, let's say Pi, Pj, and I'm gonna replace them with their average, just like we did for R. And once I do this replacement, I potentially reduce the probability of at least one birthday match. So how can I make sure that I don't do this? How can I make sure that the probability of at least one birthday match is minimized and can't be reduced? Well, to do that, we need to make sure that when we do this replacement operation, P does not change. So replacing this does not change P. And for this to happen, it is clear to see that all the values in P need to be the same. So P, not change P. So P needs to have identical values. Why? Because if they're all identical values and I select two of them, well, they're all equal, so if I select any two, they're both equal to Pi. And if I look at their average, I again get Pi. So what I'm seeing is I take two values from P and replace them with the same value. So I'm not changing P in this case. And this is what we want. We want the scenario where if we take two values in P and replace them with their average, we don't actually change P, because if we do change P, then we potentially, as we showed, we potentially reduce the probability of at least one birthday match. And so, as we just said, we want the values in P to be all the same. Now, P, the vector P, contains probabilities, and so by the axiom of probabilities, the sum of these values in P have to be equal to 1. And since we just said we want all 365 of them to be the same, each Pi must be 1 over 365.